I wanted to do just this extra video, extra example, should you feel that you need it. Plus one more that kind of comes to mind if you feel like you are not quite getting the gist of the partial derivatives. And I would love to give you an example where product or quotient rule are being used that I'm going to come up with. So, a little bit of extra example should you need it, right? I'm going to, again, the steps are the same. I'm going to find the partial derivative with respect to x of this function. I'm kind of messing with you on the notation, remember, to know what they all mean, right? Partial derivative with respect to x. Here's my function, x to the third, x squared y to the third minus 2y squared, right? Since we're taking the derivative of x, 3x squared plus y to the third. Remember, I'm working on this second one. We treat this one like a constant. Take the derivative of x squared to get 2x. And then the last one only involves y, so there we have it, a 0. So I get 3x squared plus 2xy to the third. For my partial with respect to y, I'm going to do the same thing, except now, right, what I'm working with is this one's constant, so that's going to go to 0. I'm just jumping in. I'm skipping some of the steps. You don't need them all. Plus derivative with respect to y. Keep reminding yourself, x squared is constant. Just write it. Then focus on what you need, 3y squared. Last but not least, partial derivative of negative 2y squared, right? We're going to bring the 2 down to get negative 4y. And you know me, I'm going to clean it up. If I wanted to evaluate it at a point, right? This is a great example of seeing both x and y. If I wanted to evaluate the slope of this tangent line at the point 2, 1, I'm going to plug in x equal to 2 and y equal to 1, and then I'm going to evaluate to figure out my slope. So this one's 16. Same thing over here. We can do the same thing at the point 2, 1. Plug in our values for x and y, so 4 times 1, and then put it all together, and you get 8. Right? So if we're looking at a 3D surface like these paraboloids, right? So you've got this paraboloid, you take a plane, and you see where it chunks you off this way, and then you see where it cuts you off this way, and you pick a point and you're like, oh, what's this slope? What's this slope? I know that's not the best image, but trying to give you a visual of like what we've been talking about. I do want to show you one example, at least one, where let's say we need product rule. So a little extra example. Let's say I have the function ln of x times x squared plus y squared. Let's say I want to find, let's do both. Let's find the partial derivative with respect to y, because that one's going to be a little easier, right? Everything here involves an x. So its derivative with respect to y is 0 plus 2y. So this one is a linear change. So that one will be nice. For our partial derivative with respect to x, not quite as straightforward. The reasoning because if you notice right here, we've got a function of x, ln of x times x squared. This tells us we need the product rule. Don't forget, product rule. F times g, you're trying to find its derivative. F times g prime is f prime times g plus g prime times f. So what we're going to do is, and I'm going to do it quickly, is I'm going to start by taking the derivative of the natural log. You can flip back to the first page. I did this dependent on x to help you, which is just 1 over x times x squared plus, so we're still applying that chain rule. We've done the first part, product rule. We've done the first part. Now we need to leave this one alone and then take the derivative of x squared, which is 2x. Final step, derivative of y squared. Well, that's just 0, right? So an example using the product rule, I'll have to do some simplification. I've got an x here. I can cancel out an x here. So I'm left with x plus 2x times ln of x. And there's our final answer.